Okay, so we're going to go through this example together from the checkpoint problem and see how it went when you tried it yourself. So we're starting with this um, statement at the beginning here, and we want to decide if it's a trig identity. So we're going to verify and see if we can get the more complicated side to match the less complicated side. And both of these sides look pretty awful, don't they? But usually, if you have an operation such as division, that's going to be considered the more complicated side. So we're going to go ahead and start with that as our given. So the cosecant of negative x divided by the secant of negative x is where we'll begin. And if we take our trig hexagon, so off to the side here, we'll go ahead, oops, too many. We'll go ahead and sketch out that trig hexagon to remember our identities. So tangent is sine divided by cosine, and then we're going to go across the diagonals here. The reciprocal of cosine is the secant, and the reciprocal of sine is cosecant. Then reciprocal of tangent is cotangent. And in the center, we'll go ahead and put a 1. So if I notice these negatives here, that makes me think of even odd identities. And remember, you can find your even identities by looking for the abbreviation that has an E in it, and secant has an E. So secant and its reciprocal cosine, those are even. So secant of x and cosine of x, those are even identities. Okay, even identities mean that if I have a function f of negative x, I put in a negative, then out comes positive f of x. That's what even means. So if I'm starting with a secant of negative x, that's going to be equal to the secant of positive x. If I start with a cosine of negative x, since it's an even function, that'll be equal to the cosine of x. So when I look up here, I've got a cosecant, which is not one of these two. So that means cosecant is an odd function. Odd functions, let's see if we've got some room up here. Those, when you put in a negative x into your f of x, it gives you the opposite of the function. So it brings that negative out to the front. And all 4 of these, tangent, sine, cotangent, and cosecant, are odd functions. So that means the cosecant of negative x is equal to negative cosecant of x. Right, that's my odd identity. And that's over the secant of negative x. Okay, secant, we know from our trig hexagon down here that that's an even function, and so the secant of negative x is equal to the secant of x, so we'll use our even identity for that one. So negative cosecant of x is over secant of positive x now because of the even identity. Okay, next it asks us to look for a quotient identity, and cosecant divided by secant on our trig hexagon. So here's cosecant, here's secant, and that means that cosecant divided by secant is cotangent, because remember, 2 consecutive vertices make a ratio on that hexagon. So cotangent is cosecant divided by secant. So we'll go ahead and make that substitution into our proof here. So cosecant divided by secant now will become cotangent. So we have a negative cotangent of x. Okay, then our last step should get us back to what we started with up here, which is negative tangent of pi over 2 minus x. And cotangent and tangent are cofunctions. So if I look at my horizontal, that's where my cofunctions live. I can see that cotangent is equal to the tangent of pi over 2 minus x. So I'll use that cofunction identity and change this cotangent of x into the tangent. Oops, lost my lead. Into the tangent of pi over 2 minus x. And now we have finished our verifying of the identity proof because we matched to the other side of what we started with. And so that one checks. Okay, hope that went well for you. And in the next video, we're going to move on to example 3, looking at Pythagorean identities in our proofs.